Welcome to the topic of energetics. In this chapter, we'll explore how energy is transferred during chemical reactions, why some reactions release energy while others absorb it, and how chemists measure these changes using enthalpy. These ideas help explain everything from combustion to industrial processes. Energetics A-level chemistry specification, exothermic and endothermic reactions, enthalpy change, and standard conditions. Key definitions of standard enthalpy changes. Every chemical reaction involves breaking old bonds and forming new ones. Breaking bonds always requires energy, while forming bonds releases energy. The balance between these two processes determines whether a reaction is exothermic or endothermic. Chemical reactions involve the breaking and forming of bonds, processes that are always associated with energy changes. In an exothermic reaction, more energy is released when new bonds form in the products than is required to break bonds in the reactants. As a result, energy is transferred from the system to the surroundings, causing the temperature of the surroundings to increase and giving a negative enthalpy change, H0. Enthalpy change, H, is defined as the heat energy transferred during a reaction at constant pressure, which is the condition under which most chemical reactions occur in the laboratory. Enthalpy changes are measured in kilojoules per mole, kJ mol to the power of 1, and always refer to a specified chemical equation. The standard enthalpy of combustion, Ch degree, is the enthalpy change when 1 mole of a substance is completely burned in excess oxygen under standard conditions, with all reactants and products in their standard states. The standard enthalpy of formation, Fh degree, is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. Reaction profile diagrams and activation energy, calorimetry, and the equation Q equals mCt, worked calorimetry calculations, required practical 2, measuring enthalpy changes. Reaction profile diagrams are graphical representations that show how the energy of a system changes as a reaction progresses from reactants to products. The vertical axis represents energy, while the horizontal axis represents the progress of the reaction. A key feature of these diagrams is the activation energy, EA, which is the minimum energy that reacting particles must possess for a reaction to occur. Activation energy corresponds to the energy required to break bonds and form the transition state. In an exothermic reaction profile, the products are at a lower energy level than the reactants, resulting in a negative enthalpy change. In an endothermic profile, the products are at a higher energy level, giving a positive enthalpy change. Calorimetry is the experimental technique used to measure enthalpy changes by recording temperature changes in the surroundings, usually water or an aqueous solution. The fundamental equation used is Q equals mCt, where Q is the heat energy transferred in joules, m is the mass of the solution in grams, C is the specific heat capacity, typically 4.18 J g to the power of 1 K to the power of 1 for water, and T is the temperature change in degrees Celsius or Kelvin. In an exothermic reaction, heat released by the reaction is absorbed by the surroundings, leading to a temperature rise, while in an endothermic reaction the temperature falls. Worked examples are essential for building confidence in calorimetry calculations. Consider a reaction in which 0.10 moles of a substance reacts and causes the temperature of 50.0 G of water to increase by 20.0 degrees Celsius. Using Q equals mCt, the heat absorbed by the water is calculated as Q is equal to 50.0 times 4.18 times 20.0 equals 4180 J. This energy came from the reaction, so the heat change of the reaction is minus 4180 J. To find the molar enthalpy change, this value is divided by the number of moles reacting. H equals minus 4180 divided by 0.10 is equal to minus 41,800 J mol to the power of 1, or minus 41.8 kilojoules mol to the power of 1. Key practical skills include using a thermometer or temperature probe correctly, stirring the solution to ensure even heat distribution, and identifying the maximum or minimum temperature reached. Evaluation is a crucial component of this practical, with common limitations including heat loss to the surroundings, heat absorbed by the calorimeter, and uncertainties in mass and temperature measurements. Improvements might involve using a polystyrene cup with a lid, adding insulation, or using a digital temperature probe with data logging. Hess's law and enthalpy cycles. Hess's law calculations using formation data, mean bond enthalpies, bond enthalpy calculations and limitations. Hess's law states that the total enthalpy change for a reaction is independent of the route taken, provided the initial and final states are the same. This principle is a direct consequence of the conservation of energy and allows chemists to calculate enthalpy changes that cannot be measured directly. Enthalpy cycles are diagrammatic representations that show alternative pathways between reactants and products, often using data such as standard enthalpies of formation or combustion. One common application of Hess's law involves calculating the enthalpy change of a reaction using standard enthalpies of formation. The general equation used is RH degree equals FH degree, products, FH degree, reactants. Mean bond enthalpy is defined as the average energy required to break 1 mole of a particular type of covalent bond in the gaseous state, averaged over a range of compounds. Bond enthalpies provide an alternative method for estimating reaction enthalpies using the equation H almost equal to sigma, bonds broken, sigma, bonds made. To estimate the enthalpy change of a reaction, subtract the total energy released when bonds form from the total energy required to break bonds. Remember the formula, bonds broken minus bonds formed. Born-Haber cycles and lattice enthalpy, factors affecting lattice enthalpy, exam tips and summary of energetics. Born-Haber cycles apply Hess's law to the formation of ionic compounds and are used to calculate lattice enthalpy, which cannot be measured directly. Lattice enthalpy is defined as the enthalpy change when 1 mole of an ionic solid is formed from its gaseous ions. Constructing a Born-Haber cycle involves several steps, including enthalpy of atomization, ionization energies, electron affinities, and enthalpy of formation. The magnitude of lattice enthalpy depends primarily on the charges of the ions and the distance between their nuclei. Higher ionic charges and smaller ionic radii result in stronger electrostatic attraction and more exothermic lattice enthalpies. Reaction profiles and activation energy connect directly to kinetics and the Arrhenius equation. Lattice enthalpy and Born-Haber cycles link energetics to ionic bonding, polarization, and trends in inorganic chemistry, such as the thermal stability of group 2 compounds. In this chapter, you've learned about exothermic and endothermic reactions, enthalpy changes, bond enthalpies, calorimetry, Hess's law, and reaction profiles. Mastering these concepts will prepare you for both calculations and longer exam questions on energetics. Thank you for watching.